Alright, this little interesting, really a sort of a roof truss type of system here has a variety of different loads on there. We're being asked to draw free body diagrams and select appropriate equations. In other words, conceptually solve the problem that we've been given. We're supposed to find AD, CD, and CE. And that just looks to me like it calls out for potentially cutting right through all three of them, and let's see what we get if we do that. It doesn't always work out, but we can try it, and let's see what happens. And again, I like to show all the members that are in the cut, even though that might take me a little bit longer and might look a little complicated to do that. And let's see what we've got here. We've got at B, we only have the possibility of a vertical reaction, right? And if I sum moments about K in the global free body diagram, each of the applied forces is trying to spin the system in a counterclockwise fashion. That means By has to push in the other direction for equilibrium. Hence, I know By has to be upwards here. Now, we got the applied force in the free body diagram of horizontal at A, that's 36 kilonewtons, and now we have these three possible chord forces. Now typically the top chord is in compression, so I'm going to show it that way. The diagonals, well, they're a little tricky here to kind of play with, and so I don't know what they're going to do. I'm not sure I can kind of guess very well, other than I got By, big force going up, so I'm going to guess that maybe CE is going down, has a downwards component, likewise that CD does as well. Now before I move off of that, let me take a look. I've got one force that's shown as having an X value going to the right, and I got three of them with X values going to the left, which sounds a little kind of sketchy, but it's possible that it might work out that way. So it's a weird looking truss. I'm not as confident about what might be going on with this one, but I do know that at least it's possible for this to work out the way I've got it showing. Right? Now if we sum moments about point C, then we can use that to find our force AD, because CD and CE will go away automatically, and we'll need to know By, but we can get that again from the global free body diagram. So that's how I would find AD. Right? So we got that one. Now what do we do? Oh, hey, if that worked out, why not sum moments about point D, and then we can find CE. Now when I do that, you can resolve CE into two components at point C if you want to. What I would do is slide it back up to this point A, break it into two components, and note now the moment arm of the Y component is going to be really easy. It's 4.5 meters. Ooh, that makes life a lot easier when you play around with that and do it that kind of way. You could also likewise have slid it down to point E, broke it into an X and Y component, used now only the X component because the Y would have gone through point D. There's all kinds of little clever ways to make this a lot easier. And then finally, let's see, that's AD and that's CE. How do we get CD? Well, we could come up here in some moments about point A to find FCD. And note something really bizarre that's going to happen here, and that is By goes through A, 36 goes through A, AD goes through A, CE goes through A. Holy schmoly, we're going to find when we do this that CD is going to be 0. Wow, now that's a pretty weird and wild kind of thing. And then look what's going to happen. We should have actually seen this right off the bat. And that is, go look at joint B. We've got, at joint B, we have AB, we've got BY, that's two collineal forces, and then we have BC hanging out here. and that has to be 0 because sum of forces in the x component is 0, so that actually is 0, just like DC turns out to be 0, and that's a kind of like another rule of thumb that we really haven't talked much about. If you have members, 4 of them, coming into a joint, and there's a pair of collinear forces, then what that tells us actually is that the pairs are equal. Now, be careful how you interpret what I just said there, right? That's the pair I'm talking about that has to be equal. That will have to be the same. And then likewise, this other one, I don't know if they're compression or tension, it doesn't matter. Oops, sorry. That's F1 there, and that's the second pair. F2 has to equal F2, and F1 has to equal F1. Now, F1 does not equal F2. That's not what I'm saying. I'm just saying that that has to go straight through the intersection, so to speak, because there's no other applied force to make that work out. And you can prove that another way here, too. Some forces in this rotated coordinate system here, and we're only going to have that y prime component and this y prime component, and they have to be equal and opposite. And since it's the same angle, therefore these magnitudes of these two forces have to be the same. Right, so that's a pretty tricky little one there to play around with, and it's really ultimately caused by the fact that Bx is 0, and that ripples its effect right on up the path there.